Using all 1991 birth records in the computerized National Birth Certificate Registry compiled by the National Center for Health Statistics, statisticians Tracy Clemens and Marcelo Pagano found that the birth weights of babies in the United States are not symmetric. However, they also found that when infants born outside of the typical 37 to 43 weeks and infants born to mothers with a history of diabetes are excluded, the birth weights of the remaining infants do follow a normal model with a mean of 3,432 grams and a standard deviation of 482 grams. The following questions refer to infants born from 37 to 43 weeks whose mothers did not have a history of diabetes. Compute the z-score of an infant who weighs 2,440 grams. Well, if you'd like to compute a z-score, there's a formula that you would use. And the formula for a z-score is x minus mu divided by sigma. So the data value that you're interested in minus the mean divided by the standard deviation. So in this case, the z-score that we have would be 2,440, which is our x value. The mean of this distribution is 3,432, and the standard deviation is 482. So using the calculator, I get 2440 minus 3432, and if you don't put parentheses around the numerator, make sure you do that calculation first and then do your division. So taking the previous result divided by 482 and follow the rounding that's provided in the problem. Generally 2 decimal places is fine for z-scores. Negative 2.06 is what I will report here. Approximately what fraction of infants would you expect to have birth weights between 2,680 grams and 4,270 grams? So what fraction? Fraction is another way of talking about a percentage, which in terms of probability theory, we can always interpret probabilities as percentages. So this is just another way that we're being asked to find a probability. And that probability is based off of a normally distributed set of data that was given to us back in the problem. So if I draw a normal distribution whose mean is 3,432, and the standard deviation is 482. I'm looking for a value that's the percent of values between 2680 and 4270. So between these two values, I want that area. To get area under the curve, that's when I use the normal CDF function. The normal CDF function takes up to 4 inputs. The first 2 are the lower bound and the upper bound of the shaded region. The mean is 3432 and the standard deviation is 482. So that's the order that you give. It's the lower bound of your shaded region, the upper bound of the shaded region, the mean, and the standard deviation. So let's get the calculator and find out what that is. So I hit second in distributions, normal CDF, and just start typing in the values as they're provided. Make sure to separate each with a comma, and in the end you'll get the probability 0.8938. Now if you're asked to provide a different number of decimals, follow those rules, or if you need a percentage, change it to a percentage, but this is how I will report this answer. Now, it's possible that you saw a menu when you were using normal CDF, And some of the later model calculators do that. And it's just a means to help you remember the order of the inputs to your functions. Sorry, there we go. Well, second. Oh, it wasn't using the second key. Second in vars gives me the distributions menu. Now, inverse normal CDF is what we use. My fault there. All right, normal CDF. If it gave you this menu, you just type in those 4 inputs as you see them. But don't worry about putting commas between them because the calculator will ultimately put those in for you. So just enter your inputs, and it just helps you know which order to put your inputs rather than having to memorize that. Ultimately, it just takes those values and separates them by a comma, plugs them into the normal CDF function, and gives you the result. So the same answer is given either way. Approximately what fraction of infants would you expect to have birth weights above 4,270? So above 4,270, the only thing that changes is for our distribution is the area that's being shaded. We would still use normal CDF to solve that. But the inputs to normal CDF, the lower and upper bounds change. This time the lower bound is 4,270. The upper bound, it goes on to infinity. But there's no button for infinity in the calculator, so we'll use E99, or you can use anything that's just very large in comparison to the rest of your numbers. But the mean and standard deviation are still the same in this situation, so those are still our last 2 inputs. And I'll get the calculator out. Second distributions, normal CDF. The lower bound is 4,270. Upper bound, to get E99, hit second and comma, and that gives you the E. And all this means is 1 times 10 to the 99th power, so it's just something really big. Put that in. The mean and standard deviation are not changing. Press enter and enter once again, and we get our probability. So 0.0411 to 4 decimal places. All right, lastly, a medical researcher wishes to study infants with low birth weights and seeks infants with birth weights among the lowest 20%. Below what weight must an infant's birth weight be in order for the infant to be included in the study? So we have a normally distributed set of data whose mean is 3432 still, and the standard deviation is 482. We're looking for values that represent the lower 20% of the data. So in the end, I want some value x, which is measured in grams in this case, because the mean and standard deviation are in grams, which means this axis right here is in grams. So my final answer isn't a probability or a percentage. It's a number of grams. In order to take a percentage under the curve and convert that to something relative to your mean and standard deviation, that's when you use inverse norm. So inverse norm takes 3 inputs. The first input is an area to the left. The area to the left of the score that I'm interested in, x, is 20% or 0.2. And then it accepts the mean of your distribution and the standard deviation. So when I put that into the calculator, second vars, come down to inverse norm, area to the left is 0.2, the mean is 3432, standard deviation is 482. And that goes into the inverse norm function, and we come up with the value 3026 and I'm going to round to the same accuracy as the mean and standard deviation, which is the nearest gram. So 3,026 grams.